Hey, all right, so we're going to start chapter 5. And chapter 5 is all about polynomials, and this will be the last chapter before our next midterm. So a polynomial is just like a linear function or a quadratic where it's made up of terms of x and powers of x added together. So polynomial is just a function that looks like a to the n plus a to the n minus 1, x to the n minus 1, the way down to a1x to the first plus a naught. So these a naughts through an's are just real numbers, and each n is just some number like 1, 2, 3, 4. It just tells you how high you should go. In lower degree polynomials, we would label it as like ax squared plus bx plus c. And yeah, we could keep using different letters of the alphabet here. The problem is we don't know how high of a power this is. So if this n was 27, then we wouldn't have enough letters in the alphabet to label each constant. So we just switch to a sub n's to tell us that it's just some constant depending on what n is. So some examples, like 5x to the 100 minus 1, 3x to the fourth minus 3x squared, 1 over 27, x squared plus pi are all examples of polynomials. Also, f of x equals 2 and f of x equals 0 are polynomials. We make this definition to make these constant functions and the zero functions polynomials because when mathematicians are proving theorems, they want a property like if you add two polynomials, it's still a polynomial. And so it's possible you could add two fifth degree polynomials and get just a constant out. So for example, x to the fifth plus 1 minus x to the fifth is the sum of two different polynomials, and it comes out to being just 1. Yeah, so there's three things that people are interested, or there's many things people are interested in with polynomials, but three things that come up all the time are end behavior. End behavior is what happens when we plug in very large values of x, either very large positive or very large negative values of x, and what the function is doing and what values it's going to. We also care about the roots of polynomials, so where f of x equals 0. And we care about maximums and minimums. So in 4.3, we did maximums with quadratics and minimums with quadratics. It's going to be tough for us to do maximums or minimums with polynomials of higher degree. That's actually a subject that's usually reserved for calculus. But so in this class, we'll talk about end behavior for general polynomials and roots for general polynomials. So end behavior is essentially just asking what happens when we plug in large values of x. And with polynomials, it actually has a nice answer. So we get plus or minus infinity. So it doesn't approach a constant. So that kind of tells us that the graph of the polynomial is going to look something like that. And it won't look something like that. So this is not a polynomial. We can kind of see that we should get really large values of x Because if we have something like x to the fifth minus x to the fourth plus 1, when we plug in really large values of x, they're getting huge from this x to the fifth. But with this, we can't approach a constant because they're just blowing up. Like if we plugged in x is 1,000,000, we're going to get 1,000,000 to the fifth minus 1,000,000 to the fourth plus 1. All right, so maybe there's a flaw in my reasoning here. Isn't it possible that the x to the fifth could output a large number? Then we subtract x to the fourth, which should also be another large number, plus 1. So maybe we are approaching a constant. It turns out that that's not the case. So the x to the fifth makes large numbers grow so much faster that the x to the fourth can't do much to compete with it. So for instance, if we call that f of x, then f of 100 equals 100 to the fifth minus 100 to the fourth plus 1. That's going to be a 10 followed by 10 zeros. Or sorry, that's a 1 followed by 10 zeros. Minus a 1 followed by 8 zeros plus 1. So that should equal, I think we get 9, 9. We subtracted everything else, so we get 9, 9 followed by 7 zeros. 1, 2, 3, 4, 5, 6. And actually, because we have a plus 1, that becomes plus 1. So we still get a very large number out of it because this 10 to the 10 is so much larger than that 10 to the 8th. So that's kind of the idea. We get this so-called dominant behavior. And there's some nice patterns that happen too. It splits up if if the largest power of x is an even or odd power. We call that the degree. So the degree of f is n, where n is the largest power of x. Let's see, I'm running out of space on my sheet, so I'll go to the side. And so if f of x equals x cubed minus x, then the degree of f is this largest power associated with x, so the degree of f is 3. F of x equals x to the fourth plus 1, the degree of f is 4. If f of x equals a, or let's just actually call that a number. So if it equals some number that's not 0, then the degree of f is 0. Lastly, if f of x equals 0, our textbook decides to leave this undefined. It kind of varies with which subject you're working in. So in pure mathematics, there's 2 big fields that study polynomials and their degrees. One of them is linear algebra or functional analysis, in which case it's convenient to set the degree of the 0 polynomial as 0. The other one is in this field called abstract algebra, specifically something called ring theory, where it's convenient to set the degree, the 0 polynomial equal to infinity. So it just depends. And in this class, we're going to say it's undefined and usually won't matter too much for our theorems. So that's good. All right. So for end behavior, we get two different cases if it's odd or even. So if let's see, I want to write it like that. So that's degree of f is odd, degree of f even. So odd in that sense of odd that you know, like the degree of f is like 3 or 5, 7, even being 2, 4, 6, or more. And then if the leading coefficient is positive, and if the leading coefficient is negative, then we can completely classify the end behavior. So if the leading coefficient is positive, then as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x goes to negative infinity. If it's even, then as x goes to either one, the function goes to infinity. When the leading coefficient is negative, so meaning we have something like negative 2x to the fifth, then the rules are just swapped. So as f of x goes to infinity, the function goes to negative infinity. As x goes to negative infinity, the function goes to positive infinity. And for the even case, as we go to plus or minus infinity, the function goes to, let me fix that really quick, goes to negative infinity. And so it's just saying what values the function is approaching. Is it getting really large? Are we getting really large positive values or getting really large negative values? And we can check this out on Desmos too to see some graphs. All right, so I'll share my screen, go to Google Chrome. So we can see that we have f of x equals x to the fifth plus 3. Then the degree of our polynomial is 5, so that's odd. And our leading coefficient is, you can't see it, but it's 1, which is positive. And so our function is following that rule. As we're plugging in really large positive x values, we're getting something positive out. As we're plugging in really negative x values, we're getting large negatives out. So that says we're going to positive infinity on the right and negative infinity on the left. And if we zoom out, we can see that, yeah, nothing weird is happening. Maybe one way to think about this is that when we have an odd power, when we take the odd power of a negative number, we're still getting a negative number out. So when we plug in -1, we get -1 to the fifth is still -1. And so with that logic, that's why we're getting these large negative values out. But that doesn't happen with the even powers. If we plugged in x to the fourth, then if we plug in a negative x or a positive x, they both get flipped to being a positive number. And so we get these large positive numbers out. And so it goes to infinity on both sides. And if we flip the sign, now we're getting negative numbers out. All right, so that's about it with end behavior. It's really just classifying where the function is headed to. Sorry about that.